Hello friends, myself Nalinikanta Jana, lecturer in physics, Bharaneshwar Mahavidyalaya, Utkal University. Our today's topic is about core 2 of physics honors, unit 1, rotational dynamics, and the topic is center of mass. The topic is center of mass. In your intermediate classes, you must have learnt about center of mass of a system. Before switching over to the details of CBCS syllabus, let us first discuss what is center of mass. Let us have a brief discussion regarding this. What is center of mass? Center of mass is a point at which the whole mass of the body is supposed to be concentrated. Center of mass of a body is the point at which the whole mass of the body is supposed to be concentrated. That means a body which has mass must possesses a center of mass. Every body has its own center of mass and it is a single point. The center of mass of a body may or may not lie within the body. Also, there may or may not be any mass present at the center of mass of the body. For example, in case of a ring like this, in case of a ring, the mass lies at its periphery, but its center of mass lies at the center of the ring, where there is no mass physically present at the center of mass. Also, in case of this circular ring, the position of center of mass is outside the ring. That is why what I have told, the center of mass of a body may or may not lie within the body. If we take the case of a duster, it is a body and it has also its mass and its center of mass lies within the body. But in case of a circular ring, the center of mass lies outside the ring and there is physically no mass present at the center of mass. But in case of a duster, mass present at the center of the mass. Now, center of mass of a body is different from its center of gravity. You must have known what is center of gravity. Center of gravity is a point at which the whole weight of the body is supposed to be acting. Center of gravity is the point at which the whole weight of the body is supposed to be acting. But in case of center of mass, the whole mass of the body is supposed to be concentrated. That is why center of mass is different from center of gravity. But everybody has its own center of mass and center of gravity. Practically, in almost all cases, the center of mass of a body coincides at the same point of center of gravity. That means, in almost all practical cases, both the center of mass and the center of gravity lie at a single point, but they are not same. They are different. One represents the point at which whole mass of the body is supposed to be concentrated and the other one represents the point at which the whole weight of the body is supposed to be acting. These are a brief discussion about center of mass. Now, we should go to know in detail the position vector of the center of mass of a system of particles, the coordinates of center of mass of a system particles, the velocity of center of mass, similarly the momentum of center of mass, acceleration of center of mass, force acting on the center of mass. To detailed discussion to have this, let us first find out the position vector of the center of mass of a system of particles. Okay? Let us consider a system of particles and let the system of particles be situated with respect to a coordinate system. Let us consider a system of particles. Let this one represent the Cartesian coordinate system with the origin at O. This represents the x axis, this is the y axis, and this one is the z axis. Now, let us consider a particle at this point having mass m1 and its position vector as r1 vector. Similarly, if we consider another particle at this point having mass m2 with position vector r2 vector, let us consider another point having mass m3 position vector r3 vector. Similarly, there are other particles having masses m4, m5 etc. having position vector r4. Now, the position of the center of mass of this system can be somewhere within this body. Let the position of center of mass be at this point, and I am writing this one as Cm, center of mass, and let the position vector of the center of mass with respect to the origin O is capital R vector. I am writing the position vector of the center of mass as capital R vector, whereas the position vectors of the particles are like this. Let m1, m2, m3 up to mn is equal to masses of the particles of the system. R1 vector, R2 vector, dot 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 up to Rn vector is equal to position vectors of the respective particles of the system. Let Cm is equal to position of center of mass of the system. Capital R vector is equal to position vector of the position vector of the center of mass of the system. Here we have taken capital R vector as the position vector of the center of mass of this system of particles. Now, the position vector of the center of mass of this system of particles can be expressed as R vector is equal to m1 r1 vector plus m2 r2 vector plus dot 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 up to mn rn vector divided by m1 plus m2 plus dot dot up to mn. This is the expression for the position vector of the center of mass of a system of particles. Now, we can write this as sum over I is equal to 1 to n mi ri vector divided by sum over I is equal to 1 to n mi. But sum over I is equal to 1 to n mi is equal to capital M, which is equal to total mass of the system and mi is equal to mass of ith particle of the system and ri is equal to position vector of ith particle of the system. So, the position vector of the center of mass of the system can be written as r vector is equal to 1 by m sum over I is equal to 1 to n mi ri vector. This is the expression for the position vector of the center of mass of a system of particles. Now, let us consider the case of a two body system or a two particle system. Special case for a two particle system. The position vector of the center of mass can be expressed as m1 r1 vector plus m2 r2 vector divided by m1 plus m2. This is the expression for the position vector of the center of mass of a two particle system. If we consider the case of two particles of equal masses, then what happens? If m1 is equal to m2 is equal to mc, then the position vector of the two particle system can be written as r vector is equal to m1 m r1 vector plus m r2 vector divided by m plus m. Now, it can be reduced into m can be taken as common and this is r1 vector plus r2 vector divided by 2m. m get cancelled, which implies as r vector is equal to r1 vector plus r2 vector divided by 2. That means for a two particle system of equal masses, the position vector of the center of mass lies exactly at the midpoint of the system. If we take the case of a common balance, then the position of a center of mass of that balance lies exactly at the middle point of that bar where we hold the balance in our hand. That point is the position vector of the center of mass, and it lies exactly at the midpoint of the two pans of that balance. Now, we have calculated the general expression for the position vector of center of mass of a system of particles and also for a two particle system having equal masses and unequal masses. Let us now find out the coordinates of the center of mass. Now, let us find out the coordinates of center of mass of a system of particles. Let x, y and z equal to coordinates of the center of mass of this system. If capital R vector is the position vector of the center mass, then we can write the expression for position vector of center of mass in terms of its coordinates as R vector will be equal to x I cap plus y j cap plus z k cap. This is the expression for the position vector of the center mass of a system of particles in terms of its coordinates. If we take the case of ith particle of the system having mass mi and position vector as ri vector with coordinates xi, yi and zi. That means if xi, yi and zi, I is the subscript to x, y and z, which are the coordinates of the ith particle of the system. So, if xi cap, xi, yi and zi equals to the coordinates of the ith particle of the system, then the position vector of the ith particle of the system will be ri vector, which is equal to x I cap plus y I j cap plus z I k cap. This is the expression for the position vector of the ith particle of the system. Now, we have already find out that the position vector of the center of mass of a system of particles as r vector is equal to sum over I mi ri vector divided by sum over I is equal to 1 to n mi, which is equal to capital M. So, the position vector of the center of mass of the system we can write again as the position vector of the center of mass of this system we can write again as r vector is equal to 1 by m sum over I is equal to 1 to n mi ri vector. Now, we have already derived the position vector r vector as xi cap plus yj cap plus zk cap. Also, the position vector of the ith particle as xi cap plus yij cap plus zik cap. So, putting the values of capital R vector and Ri vector from these two equations, in this equation we can write x I cap plus y j cap plus z k cap is equal to 1 by m sum over I is equal to 1 to n mi within bracket we can write Ri as xi I cap plus yi j cap plus zi k cap. Now, this can be expanded into 1 by m sum over I is equal to 1 to n mi xi I cap plus 1 by m sum over I is equal to 1 to n mi yi j cap plus 1 by m sum over I is equal to 1 to n mi zi k cap. Now, comparing the corresponding terms of I cap, j cap and k cap on both the sides of this equation, we can write now, we can write x is equal to 1 by m sum over I is equal to 1 to n mi xi, y is equal to 1 by m sum over I is equal to 1 to n mi yi, z is equal to 1 by m sum over I is equal to 1 to n mi zi. These are the expressions for the coordinates of the center of mass of a system of particles. Here capital X represents the x coordinate of the center of mass, y represents the y coordinate of the center of mass and z represents the z coordinate of the center of mass of a system of particles. Now, let us calculate the velocity of the center of mass of this system of particles. The velocity of the center of mass of this system of particles. Now, let us calculate the velocity of the center of mass of a system of particles. And to get the velocity, we have to take the help of the position vector of the center of mass of the system, because earlier we have known that velocity is nothing but the time derivative of its displacement. Here, in case of the position vector of a center of mass, we can write the velocity of the center of mass can be written as the time derivative of its position vector. So, what we know? We know that the position vector of the center of mass of a system of particles can be expressed as 1 by m sum over I is equal to 1 to n mi ri vector, and this can be expanded into as m1 r1 vector plus m2 r2 vector plus up to mn rn vector. and taking m to this side, we can write m r vector is equal to, now taking the derivative of this, we can write this as d by dt of m r vector is equal to d by dt of m1 r1 vector plus m2 r2 vector plus up to mn rn vector. Now the derivative can be obtained like this: m dr by dt is equal to m1 dr1 by dt plus m2 dr2 by dt plus up to mn drn by dt. But we know that dr by dt is the velocity. So, here we can write, in place of d capital R by dt, we can write the velocity of the center mass, because this capital R represents the position vector of the center mass. So, this equation becomes as m v, I am writing Cm as a subscript for center mass. So, is equal to m1 v1 plus m2 v2 plus up to mn vn, where v1, v2, v3 up to vn are the respective velocities of the particles of the system. Now, we can write the expression for the velocity of center of mass of the system of particles as, now from this expression we can write the expression for the velocity of the center of mass as v cm, cm stands for the center mass, as equal to 1 by m within bracket m1 v1 plus m2 v2 plus up to mn vn. And further this expression can be reduced into v cm is equal to 1 by m sum over I is equal to 1 to n mi. This is the expression for the velocity of center of mass of a system of particles, which is equal to 1 by m times the sum over of mi vi, where mi is the mass of the ith particle and vi is the velocity of the ith particle. Now, from this expression we can also calculate the expression for the acceleration of the center of mass of the system. Now, let us calculate the acceleration of the center of mass. And as we know, the acceleration is the time derivative of this velocity. So, the expression for acceleration can be obtained from the expression for velocity. We know that the expression for the velocity of center of mass is like this: v center of mass is equal to 1 by m m1 v1 plus m2 v2 up to mn vn. Now, taking the derivative of both the sides of this equation, we can write d by dt of v center of mass is equal to 1 by m d by dt of m1 v1 plus m2 v2 plus up to mn vn. But the time derivative of a velocity is known as acceleration. So, the time derivative of the velocity of a center of mass will be termed as the acceleration of center of a mass. If we write this as a center of mass, d by dt of a v center of mass is nothing but the acceleration of center of mass, and this can be written as 1 by m. Now, taking the derivative of each term, we can write this as m1 dv1 by dt plus m2 dv2 by dt plus up to mn dvn by dt. Now, further these terms can be expressed in terms of their respective acceleration. That means, dv1 by dt is the acceleration of the first particle, dv2 by dt is the acceleration of the particle having mass m2, and likewise dvn by dt will be the acceleration of the nth particle. So, we can write this as acceleration of the center of mass will be equal to 1 by m whole into m1 a1 plus m2 a2 plus up to mn a n. This is the general expression for the acceleration of center of mass. Now, this can be reduced into a center of mass will be equal to 1 by m sum over I is equal to 1 to n mi ai. This is the expression for the acceleration of the center of mass. Now, let us calculate the momentum of the center of mass of a system of particles. Now, let us calculate the momentum of the center of mass of a system of particles. We know that the expression for the velocity of center of mass of a system of particles is v center of mass is equal to 1 by m m1 v1 plus m2 v2 that are up to mn vn. Now, taking m into this side, we can write this as m vcm is equal to m1 v1 plus m2 v2 plus up to mn vn. As we know, the momentum of a particle is equal to the product of its mass and velocity. Hence, we can write this as the momentum of the center of mass, whereas m1 v1 represents the momentum of the particle having mass m1 and momentum of the second particle, and likewise mn vn represents the momentum of the nth particle. So, this expression can be written as PCM. P stands for momentum and Cm stands for center of mass. PCM will be equal to P1 vector plus P2 vector plus up to Pn vector. Thus, the momentum of the center of mass of a system of particles is the sum of the momenta of all the particles of this system. That is, momentum of the center of mass is equal to sum of the individual momenta of all the particles, and this equation can be reduced into P center of mass will be equal to sum over I is equal to 1 to n pi vector. This is the expression for the momentum of the center of mass of a system of particles. Now, we have seen here, we have also calculated here the position vector of center of mass, the velocity of center of mass, the acceleration of center of mass, and the momentum of a center of mass. Now, from this we can calculate the force acting on the center of mass of a system of particles. Now, we can calculate the force acting on the center of mass of a system of particles. As from Newton's second law, we know that force is equal to the product of mass and acceleration. Hence, here also we can write the force acting on the center of mass as F cm, which will be equal to the product of mass of the system and the acceleration of the center of mass of the system. But we have already taken the total mass of this system as capital M, and the center of mass of this system, as we have expressed earlier, can be written as MACM, where ACM represents the acceleration of the center of mass and capital M represents the mass of the total mass of the system of particles. Now, this can be written as M, this acceleration can be written as d by dt of V center of mass. As mass is constant, we can write this expression as d by dt of M V center of mass. But just we have found that M V center of mass is nothing but the momentum of the center of mass of the system. So, this can be written as d by dt of P center of mass, where the left side represents the F center of mass. Thus, we can express the force acting on the center of mass of a system of particles as the time derivative of the momentum of its center of mass. Let us consider the case of an isolated system. Special case for an isolated system, the external force acting on the system is 0, because previously we have known that for an isolated system no external force acts on the system. So, here for an isolated system F external will be equal to 0. But here what we have found here, the force acting on the center of mass is equal to d by dt of P center of mass. So, as F external acting on the system is 0, hence F center of mass will also be equal to 0, which implies d by dt of P center of mass will be equal to 0, which implies P center of mass will be constant, because we know that the time derivative of a constant is 0. So, the total momentum of the center of mass of a system of particles always remains same, and this P center of mass, that is the momentum of the center of mass, is nothing but the product of the total mass of the system and the velocity of the center of mass. Hence, this implies M V center of mass is equal to constant, which implies V center of mass is equal to constant. As the mass of the system of particles is constant, hence the velocity of the center of mass of the system is constant. That means the center of mass of a system of particles moves uniformly, because in uniform motion the velocity remains constant. Hence, we can consider that as the velocity of the center of mass is constant, hence its acceleration will be 0. That means A center of mass is equal to 0 for an isolated system. That means the velocity of the center of mass of an isolated system is constant, which explains that the center of mass of a system of particles moves uniformly. Here we have discussed in detail about the position vector, coordinates, velocity, acceleration, momentum and force acting on the center of mass of a system of particles. But in our CBCS syllabus, the topic is center of mass frame and the laboratory frame. Center of mass frame and the laboratory frame. So, let us have a comparative idea about the center of mass frame and the laboratory frame. What is center of mass frame and what is laboratory frame? It is the frame of reference whose origin is at the center of mass of the system. If we consider the case of a system of particles, then the frame of reference whose origin is at the center of mass of the system can be known as your center of mass frame. Similarly, what is a laboratory frame? It is the frame of reference whose coordinates are fixed with respect to a point in the laboratory, can be considered as your laboratory frame of reference. Let us have the comparative idea. Number 1, it is the frame of reference origin is at the center of mass of the system. Here we can write it is the frame of reference whose coordinates are fixed in the laboratory. Since the center of mass frame is at the origin of the system, hence the position vector of the center of mass of the system with respect to the center of mass of the center of mass frame is 0. That is, here R center of mass is equal to 0, because the center of mass is situated at the origin of the center of mass frame. So, the position vector of the center of mass is 0, and hence we can write the velocity of the center of mass as dr by dt, which is equal to 0. So, the momentum of the center of mass is equal to mv center of mass will also be equal to 0. That means, with respect to the center of mass frame, the position vector, the velocity and the momentum of the center of mass will be 0. And in case of laboratory frame, in a laboratory frame, the measurements are done while studying the collision of particles. In this frame, the measurements are done while studying the collision of particles. So, if a particle of mass m1 is moving with a velocity v1 along x axis and the particle of mass m2 is at a rest with respect to the laboratory frame, then the velocity of center of mass of the two particle system with respect to the laboratory frame can be written as v will be equal to m1 v1 plus m2 into 0 divided by m1 plus m2, because here we have considered the second particle to be at rest with respect to the laboratory frame, but the first particle is moving with velocity v1. So, this can be reduced into the form as v equal to m1 v1 divided by m1 plus m2. This is the expression for the velocity of the center mass of a two particle system with respect to the laboratory frame of reference. And let us find out the coordinates of the mass center of mass frame and the laboratory frame. Let us find out the coordinates of the center of mass frame and the laboratory frame of reference. To have an idea regarding the coordinates of center of mass frame and laboratory frame, let us first consider a two particle system with respect to the center of mass system and also with respect to a laboratory frame of reference. Okay, let us consider here is one particle m1, here is one particle m2, and let their center of mass lies here. Now, we can consider the center of mass coordinates of this system of two particles here like this, and this can be considered as the laboratory frame of reference. Let the origin of this laboratory frame of reference is at O, whose coordinates are x, y and z, whereas the origin of the center of mass frame is at here the Cm, point Cm, and these are the coordinates of the center of mass frame of a two particle system of masses m1 and m2. Let m1 and m2 is equal to masses of a two particle system. Let r1 vector and r2 vector is equal to this one is r1 vector and this one as r2 vector. r1 vector and r2 vector as the position vectors of the points of m1 and m2 with respect to the laboratory frame. Laboratory frame. And let this one is the r1 dashed and this one is the r2 dashed. r1 dashed and r2 dashed is equal to position vectors of M1 and M2 with respect to the center of mass frame. And this one is the R vector is the position vector of R1 vector, capital R vector is the position vector of the center of mass with respect to the laboratory frame. R vector is the position vector of center of mass with respect to the laboratory frame. Now, from the geometry of this figure, we can write R1 vector is equal to R vector plus R1 dash vector, which implies R1 dash vector is equal to R1 vector minus R vector. Similarly, we can write R2 dash vector is equal to R2 vector minus R vector. Here we have given the relations between the center mass frame and the laboratory mass frame position vectors. Similarly, by taking the time derivatives of these two equations, we can write d r1 dash by dt is equal to d r1 by dt minus dr by dt, which can be written as v1 is equal to v1 dashed minus v center of mass. Similarly, for the second particle, we can write v2 is equal to v2 dash minus v center of mass, where v1 and v2 represent the velocities for the particles of masses m1 and m2 with respect to the laboratory frame, and v1 dashed and v2 dashed represent the velocities of the two particles with respect to the center of mass frame. Now, multiplying mass m1 to both the sides of this equation and multiplying mass m2 to both the sides of this equation, we can write this represents the momentum of the particle, first particle with respect to the laboratory system, which can be written as p1 dashed minus p center of mass, and similarly the momentum of the second particle with respect to the laboratory frame can be written as p2, which is equal to p2 dashed minus p center of mass, where p2 dash represents the expression for the momentum of the second particle with respect to the center of mass frame. Now, the total momentum of the system of particles can be written as the sum of these two equations. Now, we can write, adding these two equations, we get m1 v1 plus m2 v2 is equal to m1 v1 dash plus m2 v2 dash minus m1 v center of mass minus m2 v center of mass. On simplifying these two, we can write m1 v1 plus m2 v2 is equal to m1 v1 dashed plus m2 v2 dashed minus, if v center mass will be taken as common, it will be m1 plus m2 into v center of mass. But we know that v center of mass is equal to m1 v1 plus m2 v2 divided by m1 plus m2. Now taking this, we can write m1 plus m2 into V center of mass is equal to m1 v1 plus m2 v2. So m1 v1 plus m2 v2 minus m1 plus m2 into V center of mass will be equal to 0, and putting this value in this equation, we can write this as m1 v1 dash plus m2 v2 dash will be equal to 0, which implies m1 v1 dash is equal to minus m2 v2 dash. That means the momentum of the particles are equal in magnitude and opposite in direction with respect to the center of mass frame. Hence, hereby we have discussed today about the center of mass, its coordinate, its velocity, acceleration, momentum and force. Also, we have discussed here the center of mass frame and the laboratory mass frame, and here we have calculated the coordinates of the center of mass frame and also the laboratory frame of reference. Many thanks to students.